Okay, today we're going to go over some quick applications. The goal of today is for you to learn new ways to communicate your newfound ways of linear algebra and matrices. And in particular, what I want you to do is to know that you're not just pushing around symbols when you're solving these problems. These are actual ideas that you can use to convey real-world applications. So let's go ahead and get started. The first one is about movies. And this one is all about the geometric vector form. So suppose you want to give your friend a recommendation of their movie, but your friend's just a new friend. You don't actually know anything about them quite yet, not much at all. So what are you going to do? Well, before you get started, what you're going to do is you're going to place them in a giant movie space. You're going to place them at a location. You're going to give them a vector, right? That vector might be a bunch of fives, meaning that you think that on average, they just think every movie is just average. Of course, they're going to have their own taste and that's going to change, but you don't know anything about them. So at this point in time, you are placing them in this high dimensional space as just at the very center point. And then what you're going to do is, of course, as you get to know your friend, you are going to go ahead and ask them some questions. You might ask them some questions. Now, of course, you can go down each movie and you can say, okay, let's just do you like this movie? Do you like 102 Dalmatians? Do you like this awful movie that no one else has ever heard of? And you can do that, but you'll be asking a lot of questions. So in general, there's only a certain number of principal directions or principal questions you're going to ask people. Like, for example, do you like comedies? Do you like Star Wars? Do you like dramas? Do you like disaster films? Those are the type of questions you might ask. And every time you ask a question, what you're doing is you're going to take one step in some direction. So for example, if this one is Star Wars, say Star Wars 4, that one's Star Wars 5, that one's some unknown Star Wars movie, and say this one is Titanic, right? And of course there's thousands of movies I can't possibly draw here, but one question you might ask is, do you like Star Wars? And they might say kinda. So what's going to happen is you're going to take a small step. They may say kinda, and you're going to take in your head, you're going to take a small step in some direction, right? The direction is going to be toward or in the positive direction of the Star Wars movies. And it'll be in the negative directions of movies that are, opposite Star Wars. And it might be zero in between for movies that are kind of like Star Wars and kind of not, or indifferent of whether or not people like Star Wars. But you're going to take one step. So in your mind, they now kind of like Star Wars. You're going to inch one step forward toward different types of movies. Right? And then the next one you might say is, do you like romance movies? So you're going to take one step in some direction. And they'll be like, yes. Right. So now when they say yes, you're going to take a big step in that direction. Right. So that means you're going to take one big step in that particular direction. So there's a direction indicated by a vector. Every direction is a vector. But now you're going to go further along in that specific direction. Right. And then you might ask more questions. Right? So more questions you might ask. And you'll notice what we're actually doing here is we're creating something that looks very much like the geometric vector form. So you had a starting point, and then you had these different directions. And every time you ask a question, what you're really doing is you're determining how far forwards, or in some case backwards, right? So if they didn't like Star Wars movies at all, you'd move backwards in the Star Wars direction. And at the end of the day, you're going to end up at a specific place in this very high dimensional space, right? So as of right now, let's ask let's ask one more question. Let's say, do you like disaster movies? Do you like big disasters? And they might say, not at all. So what you're going to do is you're going to take a negative step in a direction of that. Right? So all these movies, Star Wars and Titanic, have big disasters in them. So they don't like any of those movies. And then you're going to add all these up and you're going to end up somewhere. So where do we end up here? We're going to end up somewhere like 2.7, 2.7, 2.8, and maybe 4.9. Right? And then now this vector here indicates at the final step what kind of movies you think that they would like based upon the questions that you have. So the key idea of this is that every single opinion we have or rating we have can be amalgamated into a vector, and then that can be used to make recommendations. So it turns out that this is not a made-up example, right? This actually first started what's called the Netflix problem, or the Netflix prize, in about 2007. So Netflix, when they first started, when they were young, they wanted a better idea to recommend movies to people. So they put out $1 million prize, and most of the winning entries didn't approach something like this. You started out with a base rating, and then they kind of figured out what your principal directions are based upon your movie takes, based upon your previous movie rating. So instead of asking you questions, do you like Star Wars? They would just simply ask, how well did you rate the Star Wars movies you did see? How well did you rate the romance movies that you did see? And then they would take steps. They would use that to judge on how many steps you should take in various directions. Of course, this is easier said than done because you have to first figure out how many steps to make, and you have to figure out what the steps are. So this is a doubly hard problem, but at a fundamental language, all it uses is the geometric vector form to end up with what they can predict to be your movie ratings. And then they can predict and give you good recommendations of what you think you would like. So that's just one simple example of how vectors in the geometric form are used and how you can think about them. Another example of some applications are population dynamics. And this is where you have more than one thing going on that interact with each other. So this might seem like an overly simplistic example, but what we're going to do is we're just going to use bunnies and wolves. And of course, if there's a relationship between them, the population is going to depend for each one, for the number of bunnies and the number of wolves, is going to depend upon how many bunnies and wolves there are. So the bunnies just don't multiply, they're going to get eaten. And the bunnies are going to, grow if they eat more bunnies. So what happens, who wins out? Why is the professor talking about killing bunnies? Those are all questions we're going to have. So let's just give us a simple sample system. So this system might be given by something like this. So this just here means the number of wolves next year. And this might equal 1/2 of the number of current wolves. Plus 1/2 the number of bunnies. So you can think of this as some of the wolves are going to die out, but some of them he saved if there's enough bunnies to feed them. And then likewise, we can look at the number of bunnies from year to year. So the number of bunnies, they're going to depend strongly by the number of wolves. If there are a lot of wolves, they're going to eaten. But the number of bunnies is going to multiply very quickly. Just like the old adage goes, bunnies multiply. So this is the number of bunnies next year. All right, so now we have this dynamical system, and it seems very interconnected and complicated to figure out. But if we simplify this slightly, we can write this in a more compact form. And now that you see this is just kind of a linear system, we can kind of write this like this. This is now just a vector. And now this guy right here is just a matrix. There's like a hidden matrix right in there. So what's that matrix? That matrix is 1/2, minus 1, and 2 times this. So now with our newfound language of matrices, we can see that at every year, at every step, the number of wolves and bunnies, instead of being multiplied in kind of a fancy way with these fancy formulas, you can think of it as together that vector of population. This is a vector of populations. It's just getting multiplied by a single matrix, and that gives you the new one. So how this works is you're going to have a population, you're going to multiply it by a matrix, and it gives you the new one. And then you're going to go back and do it again to find out the year after that, and the year after that, and the year after that. So to put this in a geometric sense, what does this look like? We can use our before and after graphs. And here I'm just going to use kind of the positive quadrant because having negative bunnies or wolves doesn't make any sense. But we can take some of our vectors and we can figure out what happens to them. And so what's going to happen is after 1 year, what's going to happen is, well, the basis vectors are actually going to fly off. But what's going to happen is this orange one's going to grow over time. It's actually going to grow a lot. And this blue one is going to go there. And the green one actually kind of goes, where's the green one go? The green one goes to 1/2, 2. It kind of goes right here. But the red one I think is going to fall off the map. That's 1, 0. That's going to go to 1/2 minus 1. So the red one kind of goes here. So if you have only wolves but no bunnies, they're going to die out right away. And we can keep doing this. So that's after 1 step. What's going to have to happen after 2 steps? After 2 steps, you're going to have something that looks like this. And 3 steps, it kind of gets off the charts. We're going to end up with something that looks like this. And what's happening at each step here is we're multiplying by a matrix. That matrix we're multiplying by. We're multiplying each of these vectors by the matrix 1/2, 1/2, minus 1, 2. So every step, we're multiplying by this matrix. And so what's going to happen in the long term, if we do this enough times, what's going to happen is we're going to see, you kind of get this picture where the green one kind of coalesces with the orange one, and the blue one kind of doesn't really move at all. And the shape that's there is this ellipse, and quite strongly, there's one direction that you have. There's one direction you have. And in this case, that direction seems to be after 4 steps, it'll be about 2.5 to 1. So it goes from about 10 to 25. So this black vector here is about 10, 25, which means that it suggests that in the long term, you'll have about 2.5 bunnies for every wolf, right? 25 over 12. But it turns out that's actually not the best answer. That's just the case of doing a small number of cases. It actually approaches 2 in the long term, and we'll figure out as we go along how to do that. But one of the ideas is that if you understand the properties of these if you understand the properties of this matrix, you can actually understand the long-term dynamics of this otherwise complicated system. So this will be called a linear dynamical system, and you can figure out what happens to it. And what's actually quite beautiful is, despite the fact that it might seem like it matters where exactly you start, this kind of ellipse kind of gets squashed down into a nice shape. And almost no matter where you start, for almost any dynamical system, meaning no matter what matrix you pick, it's going to be very predictable in the long run. So if you know what matrix you have and you know how to study it, you can figure out what the shape is going to be. And one of the punchlines of what we're going to do throughout this course is figure out what that is, how to do that. It's going to take a lot of doing to get there, but that's one of our goals. How to figure out the long-term dynamics. All right. And the last one I want to just talk about is called counting walks. This one might seem kind of boring, right? Counting walks just means we want to figure, you might have a network. Just for the sake of example, we'll have this little small one right here. And you might want to ask, okay, how many ways are there to get from here, A, to B, from A to B in exactly 4 steps? So in exactly 4 steps, how would you do that? Now, in this case, you're allowed to repeat vertices and edges, right? Is it even possible, right? So one thing you could do is you could go 1, 2, 3, 4. You got to B in 4 steps, right? Or you could do something like 1, 2, 3, 4, right? So how many ways are there to do that? And you could go out, now you can try to list them all, right? But you'll see this gets very tedious very quickly, and it's very hard to keep track of which ones you've counted and which ones you haven't. But it turns out the answer is very simple. It just lands with matrix multiplication. So this little network here has a matrix associated to it. This is called the adjacency matrix. And the adjacency matrix in this case is simply going to look something like this. You're just going to put a 0 if there's an edge connecting them, and a 1 if there's an edge connecting them, and a 0 otherwise. So down the diagonal, no vertex is connected to itself, so we put a 0 there. A is not connected to B, but everything else is connected here, directly connected, directly adjacent to each other. So it has this matrix. And one of the things about this matrix that makes it very powerful is the number of walks, meaning the number of ways to get from I to J in exactly K steps is equal to this matrix raised to the K power, and you take the IJ entry. So this just says you're going to take A times A times A times A, and you're going to do this K times. And then you take the IJ entry. So just for emphasis, the IJ entry, we're going to apply the principle of RC Cola. This is the ith row and the jth column. All right, so just as a simplistic example, when K is equal to 1, that means how many ways are there to get from one place to another using only one step? So A to the 1 gives you the number of ways to get from one node to another, one vertex to another, in exactly one step. And sure enough, that's given by exactly this. But now what about 2? Let's just try an example. Let's go ahead and copy this guy. Let's do an example here. What about A squared? How many ways are there to get from A to B in 2 steps? Okay, for 2 steps, you can go that way or you can go that way. So we would expect the AB entry to be 2. And sure enough, if you multiply it out, what do you get? Right? I think there may be something. D to A is 1. And C to B is also 1. And C to A is 1 as well. Okay, so that should be what we get. So sure enough, you'll notice that the AB entry is 2. That codifies, signifies those 2 ways of doing that. And this extrapolates to any dimension. So if you wanted to, we could go answer our question. What's a to the 4th? And we could do it. Or even moreover, we could do a to the 15th, right? And this would seem tedious to do a matrix computation on it by hand, but the nice thing about computers is it will tell us in an instant what this is, and we can actually signify what that entry is. Okay, so for a to the 4th, we have something that looks like this. Again, this is just done using a computer. And for a to the 15th, if we use our computer, we'll end up with something like something very huge. But what does this entry specify? This means that there are 253,762 ways to get from, in our case, vertex A back to itself in exactly 15 steps. So as you walk around, you have all sorts of choices you can make. How many ways is that? It's going to be given by exactly that entry. You might say, okay, who cares about this? What's kind of cool about this is it kind of tells you who's more popular, right? It gives an indirect measure on how popular you are. If you think of rumors spreading around randomly or walking around randomly on the social network, right? Whoever has more ways of going to them is going to be more popular. So A in 15 steps has roughly 250,000, but on the flip side, D over here, D has 416,524. So it has about 50% more than 50% number of ways to get back to itself out of 15 steps. And in some measure, that means it's 50% more popular. And sure enough, it has its friends, in this case, with everybody. Right. But it turns out that on a bigger network, just counting the number of friends may not be the best thing to do. Counting who you're connected with is not always the best. You have to measure quantity against quality.